Right, so now we will talk about the second part of this class. We'll be focusing on those graph-based problems where we cannot efficiently solve it. So this is actually the formal beginning of the heuristic reasoning. How do we really deal with those very difficult real-world type of problem? Very large scale, but you still want solution within a short amount of time. Again, the definition of short is always relative, depending on the application domain. So we will see a lot of this kind of consideration later. So the model problem that we'll be using for today will be the traveling salesman problem. We can very briefly see what that is. And we're going to explore a couple straightforward ways where you can actually solve it. Exhaustive search, we already deal with that. Essentially looking at all the possibility. And random search is efficient, but again, it's not the performance speaking. Is actually not so good, right? And the final algorithm, that's really a more competitive one. This is a very common design principle. We call it greedy algorithm. We'll see how we can actually apply that in the context of traveling salesman. So this is one, I think, motivating example that we have used previously when we begin this whole semester of classes, right? To illustrate the importance of algorithm design. This is, again, the latest Winter Olympic torch relay planning. Very difficult problem because in total, as you can see, this is the actual torch relay schedule that was retrieved from the Wikipedia. You see that in total there are 80 locations. And a lot of people are involved, a lot of different considerations. So the so-called optimal route, in this sense, is complicated to be defined. It can be defined in terms of cost, in terms of some other side constraints that may be important for this particular event. We don't know all of that, but what we do know is that if just by using brute force, right, so you're just straight away looking at all the possible combination of the solution, this problem will grow out of hand very, very quickly. Right? For the case where you have 80 locations, is 80 factorial by applying the product rules. And this is 10 to a power of 118, a very large number. You have zero hope of actually solving it. So what do we do, right? So we start with a much smaller example, right? So this is the bike tour in Ireland, right? So later you'll see the reason why we actually pick Ireland as an illustrating example. So very small example, only 5 cities. So let's say our goal is actually very simple. We simply want to minimize the kilometers of the whole tour. And the requirement is that you start from one city, in this case Dublin. You have to visit all the bigger cities around Ireland. In total, there are 4 of them. And after you finish the visit, you have to cycle back to your starting location, which is Dublin again. Right? So the optimal tool, again, for this very small example, is actually very easy to spot. For example, if you go down over here, you just look down. These are 2 potential examples. On the right-hand side, and this is one potential route, but clearly you see that there's a ways of travel by making a cross. Right? Over here, you can see that this is the pair of the cross, which basically means that if you remove this cross, instead you travel through the direct distance from Dublin to Belfast and from Galway to Limerick. If you replace this crossover with the straight line over here, you can actually reduce the pass. Right, so you can very easily deduce the simple rules. If you want to manually generate the route, just avoid any crosses. Right, you just simply try to traverse all the cities without crossing into existing paths. If you are able to do that, most likely the path you generate will be of shorter distance. But this is for a small instance. For instance, where you have very large numbers of cities that you have to consider, then this particular method will not work anymore because you cannot really visualize that. So this is one example actually. Right, so this particular problem in general, we call it traveling salesman problem. This is a very famous computational problem that was proposed pretty early. You see that is proposed by this Irish mathematician, Hamilton, in the 19th century. That's the reason why you see that the previous example that we use is actually based on Ireland. Right? This is in dedication to Mr. Hamilton. So this particular problem turned out to be very important. So people have spent a lot of, some people spend their whole career studying this particular problem. And this is one example. You can see that all these little dots over here, that's the United States. All the major minor cities around the US, you have 13.5 thousand cities. And then you want to find the shortest possible distance to traverse each and every city. Right? So if you're interested in the original data set or in larger instances, you can visit this particular website over here. This is the professor who spent his whole career finding algorithm that can really solve very large scale trail enforcement problem, or simply we call it TSP. So this, for example, is one of the solution that turned out to be the optimal. And of course, you note that to obtain this particular optimal solution is impossible to use pure elimination. You have to be smarter, right? And this is really where the challenge lies in, right? How do you design a heuristic that don't take forever to generate, right? And over here you see that it still take 5 CPU year. We like to emphasize that it's CPU year, right? Which means that if you are able to parallelize the whole process, for example, instead of having a single computer, single CPU solving the problem, let's say you have 1,000 CPU solving this particular problem, then effectively you can divide this effort 5 years into a factor of 1,000, right? So then the time still is very computational intensive, but then the actual time that you take in reality might be much shorter, maybe a couple of days, couple of weeks, right? But it's definitely much better than 5 years. All right. So why do people care about really large scale problem, right? And here are some couple examples, right? For example, over here on the right hand side, this is the machine that you use to produce this printed circuit board, which is everywhere, right? If you open your cell phone, you open your laptop computer, you will see this particular board where all the important ICs that are being attached to it. The whole computing system, the whole gadget will only work if the component is properly connected on this particular circuit board. And drilling holes is used to be manually done, but now it's all done by machine. If you look at this particular problem, really the problem of drilling holes by like an automated machine, this particular problem itself can be generalized to be a trail enforcement problem. In this case, the CTs are just the hole that you need to drill. And the reason why it's a trail enforcement problem is that your machine, your drill, need to traverse the whole board to the right position, and then you have to drill down and make the hole. And basically, the sequence in which the hole should be drilled represent the sequence in which the CT need to be visited. If the sequence is being designed poorly, then it basically means that your machine is spending time traveling across the board unnecessarily, right? So just imagine that if you have a very lousy routing algorithm for the planning of the drilling, it takes, for example, like 10 minutes to traverse the whole board. You can actually improve the productivity without even upgrading any part of the machine. Just upgrade the software by generating, for example, a particular path that's 50% less distance. And if you are able to do that, it basically means that you can use exactly the same machinery, but now your productivity is increased by 50%. Right? So this is a less intuitive, but a very important process in a lot of this in industrial setting. And very similarly, if you look at this VLSI, this is a very large scale ICs, right? So I mean, all the important modern day computing devices, including your cell phone, including your laptop, rely on this kind of technology to pack as many components into the integrated circuit as you can, right? So again, over here, one of the challenges is that all these individual mini components that you put into the IC, they need to be connected by the wire, right? How do you find a path that will connect all these individual components, but at the same time with as short a distance as you can, right? Because the longer distance basically means that your power consumption will be greater, because the power will travel, the current will travel with a longer distance inside your IC. As a result, it will generate more heat. right? So again, over here, you can see that example 1, example 3, they are less obvious, but very important kind of planning you have to do in today's IC-based industry. And transportation, of course, if you are planning for logistic purpose, you are planning for like fetching your passengers, you have to certain numbers of stops you have to stop and pick up and drop off, right? So this is definitely the kind of application that we are looking at. So you see, this is the reason why, although you don't really have a traveling salesman that travel through, let's say, hundreds or thousands or even millions of cities, but in practice, particularly if you're dealing with the design of IC board, really you have to look at the case where you have potentially millions of components. That's the reason why scalability of the algorithm that's able to solve this kind of problem is actually very important. Okay, so let's see how fast this algorithm will soon explode, right? So the complexity over here that we put down is actually n-1 factorial divided by 2. This is the best case scenario when we try to solve this problem by brute force. The reason why you have this is on the next page, right? So you see that tool essentially is a cycle, and this is one example of the cycle. You start from A, you traverse C, D, E, and then you back to A, right? So if you do that, because it's a cycle, right? So this particular route over here will be exactly the same as if you begin your traversal from B, right? Because you're going to traverse all the CTs in exactly the same sequence, right? B, C, D, E, A, and then you back to B over here, right? Over here, this is you back to A. If you look at it, right, they are exactly the same, right? So if you have 5 CTs, means that potentially you can begin the cycle in 5 different locations, right? So total combination is n factorial, but you actually have n repetition that basically, although they look different, they all refer to the same cycle. So it's n factorial divided by n, it gives you n-1 factorial. We also need to divide by 2 because clockwise traversal is actually the same, is generating exactly the same distance as the counterclockwise traversal, right? So A, B, C, D, E is the same as if you do it on the other direction, which is E, D, C, B, A. Okay, so for each and every loop, you have 2 possible ways. One is clockwise, the other is counterclockwise. That's why you divide it by 2. All right, and the final complexity as a result is n-1 factorial divided by 2. So let's see how fast this particular number will grow, right? So for the case of 5 cities, which is the case that we illustrated earlier with the bike tool, is you actually don't really have a lot of choices, only 12. But this number grows quickly. As you reach 10, you can see that you have close to 200,000. And as you reach 25, it's 10 to the power of 23. Very, very large number. So definitely it excludes all the possibility of actually solving this particular problem by pure illumination. Just impossible to look at all these numbers of possibilities. Okay. So our graph lab actually comes with a TSP support. You can use a TSP graph, which is a derived class from the graph data structure. You can actually create a particular graph, right, where every time you add a vertex, the assumption is that you automatically add an edge between all the vertices to the new vertices, right? And you can actually generate a random graph as well. Right, so this is for you to, if you want to test any of your new heuristic, right? These are the data structure that allow you to do that. Right, so we have a couple of strategies immediately, right from the very beginning to solve the TSP. When the problem is very small, like the case where you're planning for your Ireland biking tool, right? Only 5 CT, you don't have a lot of alternative. You can actually use eyeball to solve the problem very efficiently. Even for the case of 25 CTs, you see that although pure illumination is almost impossible, but actually 25 CT, even to human eyes, is not very difficult to identify the optimal or close to the optimal solutions, right? You just keep to the principle where you always try not to have a crossover of passes. If you just keep to this particular principle, you can generate a particular cycle that's very close to the true optima. right? So this is the first approach, right? You can probably, for human, even a trained human, you can probably handle only up to about like 50, right? 40, 50, that's the limit of any human eyes, right? Anything beyond that, you need smarter algorithm to deal with it. Exhaustive search, of course, we already know that for the CT up to 10, maybe you can still do it. It's getting slower, very, very fast, right? And to the point where if you reach 20, roughly speaking, it's impossible to solve it using even the quickest machine. Random search is the method that simply say that you generate random solution, and then for each and every solution, you check how good it is. This is the reason why you have n over here, right? Because for each and every, in total, you have k of the randomly generated tool. You have to spend n effort to try to calculate the real cost involved for that particular tool, right? That's the reason why you have to incur this particular additional element, right? So it's very fast, it's linear essentially in the numbers of CTs, but the issue is that it completely rely on the chance. And for large instances, the chance that you're going to stumble upon a good solution, the chance of that will be very, very slim, right? So all three strategies, they are very easy to implement and very easy to think about, but in practice, they don't really work very well, right? Which is the reason why I think in today's class, I'm going to introduce the greedy principle that allow you to systematically solve this kind of problem. So TSP is actually a very specialized type of problem. A more general form of it is an optimization problem. So for optimization problem, it simply means that you have multiple ways where you can achieve the same goal, but for each and every solution that you can use to achieve that goal, you have an objective function that describes how effective that solution is, right? So all solutions eventually will reach the goal. Just like in the TSP case, all the sequence eventually will help you cycle all the CTs exactly one time and return back to the initial starting place. But all of the sequence, they carry different costs, traveling costs. So that will be our objective. You, all things being equal, if you are able to safely achieve your goal, then you will be looking for ways that's more cost effective, for example, so that your objective function value is better. In the end, I mean, if all possible, you want to optimize this. This is the reason why it's called an optimization problem. Right? So a lot of different examples occur, particularly if you are allocating limited amount of resources to achieve a lot of different tasks that's beyond your capability. Then to effectively use your resources, again, it poses optimization problem. So optimization problem is really everywhere, right? Whenever you have an objective function and you have large numbers of alternative, then finding the best possible alternative will be a difficult problem. Okay, so these are the ideal property that we want from our algorithm. We want it to be fast. We want it to be general, means that it can be used in a wide variety of problems without us having to recode or redesign the algorithm. And finally, of course, if possible, we want our solution to be close to optimal, right? But again, over here, you can see that you cannot obtain the service that's good, cheap, and fast. You have to pick any tool, right? And for very similarly, for the design of the algorithm, you can only pick two, right? Usually, you cannot have all three nice properties. So we will see that, three different kind of alternative of combination and see what we would like to focus on, right? So first, you can be general, means that you can solve a wide variety of the problem, and at the same time, you can be optimal. But the trade-off is that you see that we don't have speed anymore, right? So this tend to be very, very slow. In reality, you can really afford that, right? So brute force is one example. Just exhaustively try to search for solutions. So you don't have speed, right? So this is impractical. The second combination is that it's very fast and it can help you to reach optimal, but usually this basically means that you are very, very specialized. If you want to solve it to a slightly more general case, usually it's not possible, right? So again, if it's so specialized, you cannot use it to handle like real world cases. And again, although it's very fast, it can help you reach optimal. This is meaningless. Finally, right, this is actually the kind of objective that we are looking for. is fast and is general enough, but we sacrifice optimality, right? So given a time limit, we can always terminate within a given amount of time. So we can take it and you can actually use it for a wide variety of real-world problem, right? So this is the desired property. But again, over here, you have no guarantee that you're going to find optimal solution. So we, instead of looking for optimal, we look for solution that are good enough, right? But the problem is, how do you define good enough, right? And this is basically our focus. So heuristic idea is to basically just make a series of decisions and you just on the go, right? So you try to make the best possible decision as you can in each and every steps, but not over all the steps, because you know that if you try to make the best possible decision over all the steps, then it becomes combinatorial. You have to apply the product rules, which means that then you have to explore, for example, exponentially numbers of possibility or factorial numbers of possibility. But if you only try to make the best possible decision at one step, then your complexity usually will be only linear, right? So this is the trade-off. You don't optimize all the steps in one go, but instead you focus on the optimization of a single step, right? And because of that, you don't get global optimal solution, but again, the solution will be of reasonable properties. Not the best possible solution, but is reasonable usually. So there are two different classes of algorithm, right? The first class is what we call the greedy algorithm. You essentially try to construct the solution step by step, optimize one step at a time, right? So this is basically the constructive type of algorithm. You try to construct one solution from scratch, while for each and every additional step, you try your best, right? Without looking into all the combination into the future, but you try to make the best possible next step solution. The second type of the algorithm, which we are going to cover in the next week, is called local search. This is not constructive, right? Instead, this is for improvement. You have to start with some reasonable solution that is feasible, and start from that, the local search algorithm will gradually, step by step, improve the quality of that particular solution until you cannot improve it any further. The reason why you have a local over here is because if you want to find the best possible modification to the current solution, this is combinatorial. Effectively, you will look at all the possible solutions that's out there, and it can be exponential or it can be factorial, right? So you don't want that. So instead, you search for a much smaller space that will be in the neighborhood of your current solution. And because of that, we call this particular solution a local search algorithm. So again, this is the balance between how good the solution can be and how much time you like to spend in making each and every improvement, right? So we try to strike the balance. Okay, so again, over here, if you are serious about designing heuristic, usually for each and every algorithm that you provide, you have to prove the performance bound. It means that how bad, in the worst case, your algorithm will perform, right? But again, for the purpose of this class, our purpose over here is to use the concept and apply the concept in the real-world decision making or real-world algorithm design, right? So we will not focus on those theoretical issues. So the next step, we will try to look at how we can apply the greedy principle in designing algorithms for the TSP. Right, so we'll stop here for a short while, and then we'll resume to introduce two different greedy algorithms.